mentioned, today we will start a new topic, that is bipolar junction transistor. Okay, so you might be aware about bipolar junction transistor. So it's a new topic we will start today. Yeah, Sridhar, you're asking, just a minute. Okay, this is the topic, right? So this is our first three-terminal device. This is our first three-terminal device. Okay, so wherein we will see how it operates. So I could see your question. Get and yeah, I think it should be sufficient. Get and ESE question should be sufficient. Okay. So yeah, so you might know the main motivation behind this three-terminal device is we want to control the current in another terminal by controlling the voltage or current in another terminal. Okay, so it's like the main application of this bipolar junction transistor will be in switches and amplifiers. Okay, so we will see how it is used in switches or amplifiers. Okay, so what is the property of this transistor? It is helpful in helpful for in the application of amplification. Okay, so this is the thing we need to discuss. Okay, so first thing is we'll discuss the construction of the BJT. Okay, am I audible?
Yes.
Okay, so you see, if I draw the two-dimensional picture of a BJT, the cross section, okay, how it will look like. First, you will just give me a minute. Okay, so suppose we will talk about there are two types of BJT, right? One is PNP, another is NPN. Okay, so first we will discuss PNP for simplicity. Okay, so for a PNP structure, if you see the construction will be like first there will be a okay P type substrate. Okay, it will be acting like a collector. So over this P type substrate, they will diffuse a N region. Okay, N region. Okay, over it they will try to diffuse a P region. Okay, so this is the two-dimensional structure of a BJT, which have two pins. So this is called emitter. This is called base. This is called collector. Right? Right, Surajit? Hello. So it have three terminals. Okay. So and if you see the doping is like that, it is very heavily doped. It is also doped little less than the emitter. This is lightly doped. Okay. So if you go to understand the amplifier action, you can know why the doping is like this. Okay. So why I kept the emitter doping is very very high, then base, then collector. That will be very clear when we will see how a BJT operates. Fine. So if I want to like this is my am I audible?
Yes, sir.
So this is this is the way the BJP is constructed. Okay, but for our analysis purpose, right? So what we will do? We will code the device like this. Okay, if you caught it, how it will be like this. Okay, so first will be emitter, then base, then collector. Okay, so we will see the base region is very thin compared to the collector region. Okay, so that thing will be clear
Yes.
why it is like this. Okay? So we will understand why the doping is like this and why the base is very thinner compared to emitter and collector. Okay, so if you suppose you want to plot a doping profile, right? Since it's a P type, right? PNP, PNP transistor, right? So in P type, the doping is acceptor, which are generally negatively charged. So I want to plot the doping. Okay? So it will be very hugely doped. Okay. Then collector will be N type, so it will be little less. Okay. Then it will be then collector. It is lightly doped. Okay. So this is not to scale, just to show how it is doped. It is very heavily doped. Then base, then collector. Okay. So it is P plus plus N plus. This is P. Fine, Rajat?
Okay.
Okay. So let us now understand what is the basic of this transistor action. Okay. Okay. So for that, we will take the transistor. Okay. So for simplicity, I am not showing the depression region. Okay. So this is my emitter. Then base is very thin. Okay. For simplicity, I am not showing the depression region. Okay. So this is P plus plus. So this is P plus plus. This is N plus. This is P. Okay. Plus plus means it is very heavily doped. Okay. This is then this, then this. Fine. This is your base width. Base width. Okay. So what I want to do, in order to make you understand how this transistor is operating, right? What is this transistor actually? Okay. So first we will do one experiment, okay, to show you how the transistor operates. Okay. So the experiment is first we will do, we'll forward by the emitter. This is emitter, right? This is yes, this is collector. Okay. So we'll forward by the emitter by junction. Okay. And the collector by junction will be zero bias. There is no bias. Okay. Right. Then in this condition, we'll plot the minority carrier condition. Yes. So Surijit, what I am telling, initially assume that this collector back junction
Yes.
is very far. Okay, assume that this base to collector junction is very far. Okay, suppose it's very far here. Okay, this is my experiment. Okay, I am doing some experiment. Okay, so this is one case one. Okay, where my collector by junction is very far. Very far means what I am assuming is WB is very more compared to the length of the diffusion LB. Okay, LB is nothing but diffusion length in the base region, right? So what will happen? VEB. Okay, you see, whenever you flood bias, right? What will happen? What is the first thing that will happen? So the holes will be injected from P side to N side, and electron will be injected from N side to P side. Because of our simple p-n junction theory, we have explained. Okay, so holes will be injected from N side to P side. Okay, and electron will be injected from base to emitter. Okay, so here electron will be like this, right? And this is nothing but del Ne. See this point is nothing but del Ne. Okay, this point, you know, what is the value of this? You know this value, na? What is this value of concentration? What is the change in magnetic carrier? See, the electrons have been injected from base to emitter, right? So what is the value here? We know del Ne is equal to N. No, Np0 is equal to exponential of VV by Vt minus 1, right? I don't know.
Yes, sir.
Yeah. So this is the value. So the carrier concentration at the junction will depend upon the how much your emitter to base bias is. Okay, and this Np0 is Ni square by doping in the emitter region, right? So this Np0 I can write is nothing but your Ni square by doping in and emitter region. I mean donated Ne. Okay, let the doping in emitter is Ne, right? Since Ne is very high, so it is like this. And what are you like? How are you understanding? So the holes will be injected from emitter to base, right? So it will be like this. If I want to draw the profile of a hole, how it will be? It will be since I'm assuming the holes will be injected from emitter to base, and in the base, you know what will happen? The holes will be diffused, right? While diffusing, they will recombine with the electron, so the concentration will go on decreasing. I don't know. And
Yes,
if the length of the junction is very far, right? If my WB is very large compared to the LB. The LB is nothing but diffusion length of the hole in the N region, is nothing but base, right? So LB is the diffusion length of injected holes that have been injected from emitter to base, right? The diffusion length of holes that have been injected from emitter to base, since it is very small compared to the double base, what will happen? In the junction, almost all will be combining, right? So, I don't know. This is case 1, right?
yes, sir.
Yes, here is complete. Okay. So, this is the case 1. Okay. So, now, what will happen? Let us take a case. If you just, this is a second case. So, let us take the next case. Here, are you there? Okay. We moved the junction towards little bit closer, right? What will happen? Tell me. Siri, are you there? Siri? Siri? Okay. So, you tell me, Surajit. Since I have taken the junction from right to left, okay, this is case 2, okay, what will happen? This point, nothing but your del P in base, del P. So injected holes from emitter to base. Surajit, am I audible? Sorry, Siri,
Yes, sir.
Siri, you are there?
Yes, sir. Yes, sir. Right now, just
Yes.
came.
Yeah. So
Actually,
let me just
but
brief
still
you.
I'm-
Sir,
Yeah. Please tell me, Surajit. Surajit, are you telling something, Surajit? Okay, so Siri, let me just brief you. So, see, this is my, we are starting a BJT chapter. Okay, so this is the structure of my PNP transistor. Okay, where I am assuming the emitter is very heavily doped, then base, then collector. Okay, then we are doing one experiment. What we are doing? We are applying a Faraday wires in the emitter to base junction. Okay, and initially what we are assuming, the junction is very far away. Very far away means very far, very more compared to the diffusion length. Okay, so in that case, what will happen? You know, the holes will be injected, and when they recombine, the concentration will go decreasing like this. Okay, right or not? But the first case is the junction is very far compared to the diffusion length. So the holes have been injected from emitter to base, and if you plot the concentration, it will like this. Right, Surajit? Surajit, fine. And if you see, what is the slope of this junction here? What is the slope of this carrier concentration? Surajit, what is the slope of this concentration? Surajit, what is the slope of the concentration here? Hello? Surajit, you are understanding?
Yes, sir. I am audible, sir.
No, you're understanding what we are doing. Just to have forward junction, you know, in a PN junction theory, whenever you forward wise, holes will be injected from emitter to base, and electron will be injected from base to emitter, right or not?
Right.
So these holes have been injected. Since the junction is very far away, case one I'm just doing an experiment. Okay, so since I'm doing an experiment, junction is very far away. So if you plot the excess carrier concentration, right, like we have plotted in your this one in PN junction, so it will be like this, na, right? Hello.
Hello.
Yeah, it should be like this, right?
Right.
Yeah, and since the junction is very far away, if you see the slope of the carrier is almost zero here.
Okay.
See, since the junction is very far away, so we are doing an experiment. Okay, so in this experiment, the first case is the junction is very far away. Okay, so what is the case? What is the thing happening? If you want to show the flow diagram, okay, see the holes have been injected from emitter to base. So the holes have been injected from emitter to base. Okay, this is creating current that is called IEP. Surajit, clear? Surajit?
Yes, sir.
See, the holes have been injected from emitter to base, okay, creating a current, right? That is nothing donating as a IEP, right? And the electrons also is injected from base to emitter, like, right? So electron will be injected from emitter to base. Electrons will be injected from emitter to base, right? So that is nothing but my IEN.
Yes, sir.
Okay? So the IEP is the current due to the injection of holes from emitter to base. IEN is the current due to injection of electrons from base to emitter. Okay, and we know since the electrons are more here, right? After they injected here, right? They will recombine with the holes, right or not?
Yes, sir.
Yes. So then they will recombine with the holes here. Right? Holes recombination. Okay. And this contact, emitter contact, okay, is providing the holes that have been injected, right? And also providing the holes which have been lost because of the recombination with the electrons injected from base. Here, this contact is providing
Yes, sir.
all the holes that have been injected from emitter to base, and also is providing all the holes that have been recombined with the electrons. That is right? Getting or not?
Yes, sir.
Yes. So now you see what happened. Since the holes have been injected in the base, right? And I'm assuming base is very far away. The junction is very far away, right? So they will recombine with the electron in the base, right or not?
Yes, sir.
They will recombine with the electron in the base, and okay. So the base contact, what is it doing? It is giving the electrons that have been injected from base to emitter, and also is giving the electrons that have been lost because of the recombination with the holes, right?
Yes, sir. Exactly.
Yes. And since the slope is zero here, right? Slope is zero, right? Because the junction is very far away, right? Since the junction is very
Yes, sir.
far away, slope is zero. So you see the current in the collector, okay, I can say that it will be ICP will be zero. Initially it is zero, I don't know, because all the holes after reaching the junction already almost all are lost. There is no slope here. I don't know. So
Yes,
the
sir.
current is mainly because of diffusion, right?
Yes, sir.
Yes, and since almost all have been recombined and the slope here is almost zero, so the current is zero initially, right?
Yes, sir.
So the ICP is not there. Okay, in the first case. Now, what I'm doing, let me put the junction little closer to this. Okay, now again plot the same thing. Okay, will there be any change in the, so suppose go to case 2. Okay, this is case 2. Let us go to case 2. This is my case 2. Okay, I am pushing the junction towards left, right? So this is in case 2. So will there be any change in the del NA profile?
At junction it will not change, sir.
No change. No, even the profile also will not be changed because the injection of electron from base temperature will be same only, right? Even if you put the junction here and there won't be any change in this profile. I don't know.
The same.
Voltage same, so the value will be same, and see this value depend upon the base emitter voltage, right? Like this. This is the equation. Okay, so the value at the junction depend upon the voltage applied. Okay, now what will happen to the whole profile in this base junction? It will be like this because this will remain same. Okay, so in second case you can see the slope is not zero. Okay, so some part of this since the slope is not zero, okay, so they will diffuse towards the collector. That will constitute me ICP. Clear? Hello?
Yes, sir.
Yes. So
Yes,
suppose if I take
sir.
a third case where WB is very, very less compared to LB. Okay, so I'm taking very thin base. So let us take this case. Okay, this is case 3. In case 3, what I'm putting, the WB is very, very less compared to LB. So this will remain same. So again it will be like this. Right? Let's put junction here. Let's put junction very, very near to the thin. So we'll get, okay. So we'll get almost straight line. I don't know. Yeah, tell me.
Straight line.
Yeah, so almost we'll get straight line. Okay. So this is the case. In third case, you see the slope, some part of the whole is recombining. Okay. And since the slope is not zero, right? So majority of this will be going to the collector. So it is giving me a current ICP. Right? I don't know.
Yes, sir.
Yes. So you can see, even if my collector to base junction is zero bias, there is no bias. Okay, there is a current ICP in the collector junction because of a forward bias in the base to emitter junction. Okay, so a current in collector to base junction which is zero bias from base to emitter junction. Okay, nothing but transfer of current from emitter base to collector is nothing but transistor action. Fine. So for the transistor action to be successful, what is the criteria? The base should be very, very thin, right or not?
Yes, sir.
Yes. Also, since the collector current is constituted by the holes injected from base to emitter to base, okay, and this
We had
part,
to.
yeah, this current IEN is not helping us giving the collector current, okay, so this should be very, very less, right? This should be very, very less because it's not helping me to giving the current at the collector, right or not?
Yes, sir.
Yeah. That's why I initially told the dropping of emitter region is very, very high. Since it is very, very high, that's why it can be very, very low, right? Okay, so since I told
Oh,
doping is very high, that's why this can be small because this current is not helping me. It's just giving me. This is just wasting my efficiency. Okay, so I can say this IEN is not desirable. Okay, so since IEN is not desirable, so del NB should be very, very small. So to make del NB very, very small, NE should be very, very high. Clear? Hello.
Clear, clear.
Clear. So serially you have to understood. So the forward bias junction in base to emitter giving a current in the collector terminal. Okay, because because of the slope here is not zero, and whatever slope is there, the diffusion current is going to the collector. Okay.
Right.
Right. So this is not nothing but my transistor action.
So transistor. What's that word actually?
Transistor action.
Okay.
Okay. So let me show you mathematically how it is happening. Okay. Suppose what we are doing. Suppose we. So what is the criteria for this? What is the criteria for this transistor action? So let me ask the question. Okay. So then DEP is equal to constant. Okay. What you are doing? Double by LB. What you are doing? Decreasing. Right? Not here. What you are doing? You are decreasing the base width. Okay. So what will happen?
Yes, sir.
Yeah. Just a minute. So so are decreasing. Okay. So what will happen? You tell me. So IE, the emitter current, right? So emitter current is what? Nothing but your IEP plus IEN, right or not? Emitter current. Clear? Equal to IEP is the injection of holes from emitter to base plus injection of electrons from base to emitter, IEN, right?
So negative is included, right, sir?
IEN. Which negative? Since I'm see this is the whole current. This is the whole current. Okay, so whole current should be like this only, right? And electrons is flowing like this, so current also should be like this. So it's right? What is your doubt? So what is your doubt? See, this is
Clear, sir.
yeah. See, this part is the injection of holes from emitter to base. This part is the because of recombination in the base in the emitter, right? This is my emitter current. Emitter current is nothing but it providing the holes for recombining with the electron plus providing holes for injection to the base, right? So this current IE is nothing but IEP plus IEN. Fine. So then my question is, what is happening? Suppose VEB constant and WB decreasing. Okay, what is happening to my IEP? IEP, what is happening? Slope is increasing, I don't know. In this region, slope is increasing or not?
Right.
So my current is diffusion current. So it depends upon the concentration gradient. So it is also increasing, right? Right. So
Right.
and what is happening? IEN? IEN is not changing, right? IEN is constant.
Constant.
Because you see the concentration profile here is remaining same even if you move the junction here, right or not?
Right.
Right. So what will happen to my IE? Increase, na?
Yes.
Because IEP is increasing, so I should be increasing, right?
Sure.
Yeah. Then what is about collector current is equal to ICP? Okay. Initially it is 0, right? 0 when WB is very, very large compared to LV. In the first case it is 0, right? Then it is go on increasing because the slope here is go on increasing, right? So ICP go on increasing, so IC also will go on increasing. I don't know. Hello?
Clear.
Yeah. Then what is my base current? IB is nothing but, you see, IB is nothing but IEN plus this recombination current IR. I don't know. Base current. So is IEN plus IR, right? So you see, if you go on decreasing the junction if you go on decreasing the base width, what is happening? The number of hole recombination is decreasing, right or not? See, in case 1, almost all holes are recombined. In case 3, see, very less number of holes are only recommended. Here, only very less number of holes are recommended. Right or not? Hello?
Clear, clear.
Surjit, are you getting? Surjit? Okay. So here you see, if you see approximately the area under the concentration profile, right, will give you the recombination, right? So how much? What is the recombination current? Recombination current is nothing but whenever holes is injected, how many of them is recombined, right? So if you decrease the base width, right, if you see, so the recombination current IR is proportional to the area under the theory. The recombination current should be proportional to the number of charge recombined, right or not? Hello?
Clear, clear.
Yeah. So if you see case 3, so IR is proportional to number of carrier recombined, right?
Right.
And so if you see in case 3, almost all holes are recombined, right? But in case 1, where the junction is very, very close, right? So the recombination is very less. Recombination is proportional to the carrier concentration under this profile,
Yes, yes.
right? So it is almost proportional to the area under this concentration profile, right or not?
Right. Sure, sure.
So this IR is happening. What is happening if I go on decreasing this double by base width? What will happen to my IR?
Go on increasing or decreasing, sir?
If I go on, this is the condition. See, if I go on decreasing my base width,
Yes, yes. So area will also reduce.
so this will
So
reduce,
that
na?
reduce, sure.
So base width also, current will also reduce. Right or not?
Right.
Right?
Right.
So we have seen a third wise junction, right, creating a current in the neighboring junction, right? Even though the junction is zero bias, right? So what I'm telling, a forward bias junction creating a current in the neighboring junction, even if this is zero bias, right? As you go on decreasing the base width, clear? Right? Hello?
Clear, clear.
So then we'll define some term. Okay, first is called gamma, nothing but emitter injection efficiency. Okay. So what is the emitter injection efficiency? Like out of the carrier injected in the junction, how much of this efficiently transferring to collector? Okay. Getting theory? What is emitter injection efficiency?
It should recombine less, right, sir? So injection efficiency is
No,
the
no, no.
factor of
Injection means injection in junction. I did not enter into base at all. Okay. Surjit, are you there? Surjit? So theory, the emitter injection efficiency means how much of the injected carrier is across the junction, okay, going to the collector. Okay, so it is the injection efficiency. Injection means how much of injection across the junction is helpful. Okay, so it is denoted as IEP divided by IEP plus IEN, right? So
right.
what is the meaning? The total injection is IEP plus IEN. Out of that, only IEP is helpful. This is determining your injection efficiency. So across the junction, the total injection is nothing but IEP plus IEN. Okay. Out of
Yes.
that, only IEP is helpful for me. Right. This is the injection efficiency. Right. So a high efficient emitter should be injecting more IEP and injecting less IEN. Clear?
Right, right.
Okay. So are you getting? Okay, so it will equal to 1 by 1 plus IN by, right? Right?
Right.
So H WB by LB is reducing, right? What happened to this IN? Is constant, right? I told you IN is constant, right?
Yes,
IEP
yes.
is increasing, right? Hello?
Yes, yes.
So as I go on decreasing the WB by LB, the IN is constant, IEP is increasing. So what is happened to this ratio? It is decreasing, I don't know.
Yes, sir.
So this injection efficiency will be going towards 1, means it is becoming more efficient, right?
Right, right.
Right. So meaning of this, are you understanding the emitter injection efficiency? So out of the injected carriers, right, IE and IEP, only IEP is helpful. So to increase the injector efficiency, IEP should be more, IEN should be less. Okay.
Clear.
This is nothing but your emitter injection efficiency. Okay. So this may ask, they may ask you in exam, what is the emitter injection efficiency? Okay. Now there is something called B is equal to base transport factor. Okay. It is defined as ICP by IEP. Okay. So what is base transport factor? It is defined by ICP divided by IEP. So out of the carrier injected into the base, how many of this is transported across this base junction and passed to the collector? It's base transport factor. Getting? So out of the injected holes, how much of them is transported to the collector junction? This is determined by base transport factor. Clear?
Okay.
Hello?
Okay. Okay.
So this is what
Yes,
ICP by.
sir.
Yeah, sorry, tell me. Any question?
No, sir. No, sir. Yes, sir.
Okay, so this is my best transport factor. Okay, so ICP by IEP. What is ICP? So out of IEP, some current is passing because of recombination. The remaining is going to the ICP, right? So ICP is nothing but IEP minus I recombination current, right? By IEP. Clear or not?
Clear.
Clear. So it's equal to 1 minus IR by IEP. Okay. So as we go on decreasing the base width by LB, what is happening to IR? IR is what happening what? So tell me, sir, you tell me. If I
It's
go on
decreasing.
decreasing, what is happening to IEP?
IEP is going to increase.
Increase. So what is happening to this ratio is decreasing, right or not?
Increase.
So this is going towards 1.
Yes, sir.
1. So if you make base very, very thin, what will happen? Almost whatever carrier you have injected, most likely they will reach the collector junction, right?
Sure.
So what is the condition we want? So for a better efficiency, then what is the necessary conditions? The first condition is we want the emitter injection efficiency should be very, very high, right? So for that, what is the condition? The IEN should be very less compared to IEP. Okay, so conditions are okay. For emitter efficiency to get make 1, okay. First condition is IEN should be very less compared to IEP. Okay. For making that, what you have to do? You have to the doping of emitter should be very, very high, right? Because
Yeah.
this depend upon the doping of emitter, right? So that means NE should be very, very greater than to NB. This is the first condition for BJT transistor. Here, fine. Since when my doping here is very, very more, this point here is NI square by ND into exponential of this voltage. So NI square by NE. This is NE is very, very high. So this can be small, and so this point can be very small, right?
Right.
Right. This is the first condition. What is the second condition?
Sir,
Second condition is what? Yeah, tell me. Second condition is
yes.
the best transfer factor should be,
the amount of
yeah, Surajit, your voice is not audible, Surajit. Not audible, Surajit, not audible.
after recombination, the amount of that are reached at the WB, how they reach when
Actually, Surajit, voice is very breaking actually. Your voice is breaking. You can
I think I
just
think
share you understood.
yes, I think Surjit should type this because it's some
Yeah.
issue is there.
So you type your question, then we will answer. Okay.
But we can also see the
Yeah.
doubt.
Yeah.
We
So
can understand that.
you type your answer. Okay. Type your question. Okay. So what is the second condition? The second condition is the base transfer factor also should be very much 1. Okay. For that, I want my recombination should be very less. Right. So what is the condition? I want to make my WB is very less compared to LB. Okay. These are two conditions. Right. To make my transistor action successful. Right. Fine.
Right.
Fine. Na?
Yes,
Okay.
I just also want to hear that doubt.
Yeah. So it should type, then we will answer the question. Okay. Fine. You have any doubts, Suraj?
No, exactly clear.
Okay. So these are the two conditions for my transistor action. Okay. Fine.
Fine.
There is anything, one more thing is called beta. Okay. Beta is nothing but the collector current divided by base current. Okay. So I can write like this: IC by IE by. Sorry. I did a mistake. Okay. We know gamma, right? We know this gamma is nothing but Nielsen efficiency. Beta is nothing but base transfer factor, right? So this gamma is nothing but
Sir, this actually I heard previously about this high amplification like factor. So like this is said that beta is close to unity.
no. I never say beta is close to unity.
In the earlier equation, like
No. I told base transfer factor. That is not beta. Beta will come back. Okay, what are you telling? Sir, after recombination, the rest amount of holes are reaching at XB. And now they are to reach the collector side when they make. Okay. So, see, Surajit. See, what is his question? Surajit's question is, we telling that we are telling the ICP is the injected carrier minus the recombination current. Okay. So what it is telling, after it reach the junction, right? How they cross the junction, right? Even if it is zero bias. That is the question, right? Surjit? The question, yeah, the question is how they cross the junction after reaching here and pass to the collector side, even if there is zero bias. Okay. So you see your means Surjit, we know in a PN junction, right? This is my NP, right? This is my NP. right? So the NP, we know in N side we have positively charged depletion region. In P side we have negative charge depletion region, right? So the electric field is like this, right or not? Right? So this built-in electric field, which I did not show here, okay, shifting all the holes that is reaching the engine junction. Okay, so this built-in electric field in this junction here, which I did not show. Okay, this built-in electric field is pushing all the holes that reach in the junction to the collector side. Fine. So is it now? This is a built-in electric field. Okay, helps you to transport all the holes from in the across the junction. Okay, because this is positive, this is negative charge, there is electric field here. Fine.
Yes.
Yeah. Tell me. Your voice is not audible. Again, you type. So my answer is the built-in electric field is helping to transport the carrier across the junction in this, because these are the holes, right? These are the holes. Holes can be passed because this is the electric field. Okay, it will push the hole across the junction. Okay. So who understand? Who understood? Yeah. You type. Sorry, you type your question. Okay. So we have understood what is called gamma. Gamma is nothing but your IEP by IE. We understand best transport. This is B. Sorry, this is not beta. Okay, this is B. Best transport factor. Okay, best transport factor is nothing but your ICP by IEP. Okay, there is another factor called alpha. Alpha is nothing but your ICP by IE. Okay, so this is emitter injection efficiency. This is best transport factor. Okay, alpha is another term which is nothing but ICP by IE. So what is alpha? See, emitter injection efficiency is nothing but IEP by IEP plus IEN. Best transport factor is ICP by IEP. Then ICP by IE is nothing but alpha. Okay. So how it will be? So ICP by IE nothing but is equal to IEP. Okay. So equal to IEP by IE into ICP by IEP. Okay. So this will get cancelled. I'll get ICP by IE only. Right or not? Right. Okay. So this is equal to nothing but gamma into best transport factor. So this alpha is equal to gamma into beta. This B is not equal to beta. It is best transport factor. Remember this. Okay. Okay. And gamma is injection efficiency. Okay. Fine. Siri, fine.
Fine.
Fine. So what is beta? As you asked, this beta is nothing but IC by IB. Okay. So if I multiply IC by IE divided by IB by IE, I can do like this, equal to IC by IE divided by, what is IB? IB is nothing but IE minus IC. IB nothing but minus IC divided by IE. Okay, is equal to IC by IE divided by 1 minus IC by IE. Clear? So what is IC by IE? I showed you.
Alpha,
IC by
alpha.
IE, nothing but alpha, right? Equal to alpha by 1 minus alpha. This is your current gain, beta. Not, okay, this is nothing but your IC by IB. Fine, theory?
Clear, clear.
Since alpha is almost terms to, since alpha comes to 1, because we know beta
Inductor
comes to 1,
efficiency and
resistance
beta.
to 1, so alpha comes to 1. Okay, so as alpha comes to 1, so beta is very high. Okay, beta is very large. Okay, so now we will understand what is the effect of. So now we have taken a case where the collector base junction is 0 bias. Okay, now we will take two cases. What will happen when it is forward bias? What will happen when it will be reverse bias? Fine. So effect of collector junction bias. Reading the question. Okay, so we will take a transistor. Okay, so let us take transistor. Okay, okay, so this is nothing but your P plus plus N plus P. Okay, so earlier we have discussed this. This is nothing but your forward bias. Okay, VEB. Okay. Now let us apply another forward bias to the junction. PCB than 0. Okay, so we will assume that this double B is very small. Okay, from now onwards, if not mentioned, okay, I'll assume this condition. Okay, I'll assume this is there. Okay, so from now onward, I'll assume my base is very thin compared to the diffusion length. Fine. Yes. Hello. Siri, am I audible? Hello.
Hello, you say, sir?
Yeah. So from now onward, I will take this condition as true. Okay. These two conditions, all are conditions is true from now onward. Okay. So then if if LB, okay, and VB is constant, okay, then we will see what will happen if VC is increasing. What will happen if VCB increases? Fine. So let's take the case. Okay. So let's take a condition when VCB is equal to 0. Okay. So first condition we will take VCB is equal to 0. Okay. So again we will plot the concentration, right? This will be your del NE. Okay. So when VCB is equal to 0, it will be like this. Okay. This is del. Okay. So this case is nothing but condition 1. Okay. VCB equal to 0. Okay, so now we'll take a case when this case when BCB is greater than 0. Okay, so guys, you tell me what will happen when BCB greater than 0, right? Nothing will happen to del any, right or not? Hello? Hello?
Audible, sir.
Yeah. So this nothing will happen to del any, and you see what since this junction is forward bias, right? So it will emit holes from this is emitter, this is base collector. Okay, so holes will be injected from collector to base, right or not?
Right.
Right. And electron will be injected from base to emitter.
Sure.
So then first I will plot the electron profile like this. Suppose electron will be like this, somehow like this. Okay. This is my del N C. Okay. This is the excess electron or magnetic carrier in the collector because it has been injected from base because of flood bias. Fine. So, hello.
Excess.
Excess electron in the collector because of injection from base to collector. Because
Okay.
right? So base will inject electrons, right?
Sure.
Then also it will inject the holes. Suppose the holes will be like this. Suppose I don't know. Suppose holes will be like this. I don't know how it will be. Okay. Suppose it have injected the holes like this. Depending upon the since it is high bias. Okay, it will be little bit less. Okay, because we assumed this is heavier dope than compared to this, it is less. Okay. Now if you want to plot the net, right? Net will be case 1 plus case 2 na. If I say this is the injection of 2 is the injection of holes from collector to base. Now if I want to put the net concentration, right? Net concentration. What will happen? Net will be 1 plus 2 na.
Yes, sir.
Right? So it will be like this. Okay. If you add this plus this, so if you see it will go on increasing like this, here it will be like this. Okay. Okay. So this is the condition 2.
Actually, the level should be little bit low, right, sir? Because of those two graphs, if we look.
Yeah. So because this two graph, okay, what will happen? Let me tell you what will happen. Okay. So the concentration profile will be like this. LA2 will like this. Okay. Now what will happen? This. Now what will happen? This will be here. Here, case 1. In case 2, it will be like this. Because it is summation of the holes injected from collector to base plus holes injected from emitter to base. So the profile will be like this in second case. Fine?
Fine.
Fine. So now you can tell me. Now I'll do the flow diagram. Okay. So what is the flow diagram I will do? So let me do the flow diagram for you. Okay. You see the holes have been injected from emitter to base. Okay. This emitter will inject holes. Okay. This is nothing but your IE, EP, right? And the electrons have been injected from base to emitter, and they have gone and recombined with the holes. Sorry. Right. So this is IEN, right? And the holes injected here, right, will recombine with the fine. Okay. So this base will inject holes, inject electron from base to emitter, and it will supply electrons which have been lost because of the recombination with the holes. Fine. See, the emitter injected holes and also supply the holes which have been lost because of the recombination with the electrons. Right. Similarly, the base injected the electron from base to emitter and also supply the electron that have been lost because of the recombination. Fine.
Fine.
Fine. So now you see also this base have been injected the electrons, right, like this to this junction. Okay, this is ICN. right, which earlier not there, right, and also this base, because there is a slope here, right, it have injected holes, right, and both of them here will combine again here, right. So this is your ICP, right. So you can see the holes have been injected like this. The electrons are also flowing like this. Okay. Class আছে 15 মিনিট ফোন করছি, ক্লাস আছে 15 মিনিট ফোন করছি। হ্যাঁ, so you see now at the junction, right, the holes have been injected like this, and so also the electrons have been injected, right. The electron and hole have been injected in the same direction, right or not?
Right.
Right. So if I want to draw my emitter current equal to IEP plus IEN, right. So as BCB increases, okay, what will happen to my IEP? Since the slope here is decreasing, what will happen to my IEP? IEP is nothing but depend upon the slope, right? See, IEP is the diffusion current in the base because of the injection from emitter, okay. So if you see the slope here is decreasing, right, case 1 to case 2, the slope is decreasing or increased? Decrease. So what will happen to my IEP if you go on increasing BCB? Huh?
It will decrease.
Decrease. What will happen to IEN? It will be constant, right? And
Right.
what will happen to my IE? I will decrease, na? Because IEP is decreasing, right?
Right, sir.
So what will happen to my IC? My IC is nothing but ICP minus ICN modulus, because you see the holes have been injected like this, and also electrons is diffusing like this. Both are in the same direction, na? Right? Right. So the current will be opposing each other.
Yes, sir.
Yes. So ICP will decrease because the slope is reducing here from comparison from case 1 to case 2. The slope is decreased, so ICP will decrease, right?
Right.
Right. And if you go on the third bias, then the ICN will increase. ICN is nothing but the injection of electron from base to emitter. So it will increase because if you increase third bias, right?
Clear, sir.
So what will happen to my IC? IC will decrease.
Yes, sir.
Right. So then what will happen to my IB? My IB is nothing but IR plus IEN plus ICN, right? So this IB is providing injecting electron to the emitter, injecting electron to the collector, also providing the recombination current, right?
Yes, sir.
So from case 1 to case 2, you see I have more number of holes here and more number of recombination here. The area under the concentrated profile is more or not in case 2?
Sure.
So what will happen to my recombination? Will more?
More.
So recombination will be increasing, right?
Right.
And what will happen to my IN? IN is constant because this is constant. So this is constant. And ICN is nothing but the injection of electron from base to emitter will go on increasing, right? Right. So what will happen to my IB? IB will go on increasing. Getting? You see, whenever the collector bias is forward bias, what is happening? My emitter current is decreasing, collector current is decreasing, and IB is increasing. Okay. So it is destroying your transistor action, right or not? When I forward bias the collector bias junction, it is destroying my transistor action because I want more of my emitter current to reach my collector current, right or not? So there may be a point when ICP is equal to ICN, the collector current will be 0. There won't be any current, right or not?
Sure.
Since they are opposing, there may be some forward bias at which both will be equal, so my current will be completely 0, right? So the collector based forward bias is destroying the transistor action. Right or not?
Right.
Right. So this will happen when I forward bias the collector. Okay. When VCB is greater than 0, this is going to happen. Okay. So it's called forward bias. Okay. So
is this case anything useful in real life application like this?
yeah. So this case is called transistor. This is called saturation. Okay. When you will see the IV characteristic, you will know the saturation region is used for switching application. Okay, like it's like completely on. Okay, so the saturation will be helpful for switching application, not for so see the saturation region. This is called saturation region. Okay, saturation helpful in switching. Okay, not at all helpful for in amplification because you know for amplification I want the current from emitter to reach the collector. Okay, which is not happening here. Okay, so it can't act as a amplifier at all. Right or not?
Sure.
Okay? The current should reach from emitter to collector, no, but it is for amplification. Right or not?
Right.
Right. So why it is called saturation? Because the base is having more number of carrier compared to the zero bias or reverse bias. Since the base is having more number of carrier, I can say the base is saturated with carrier. That's why it is called saturation region. Okay.
Right, sir.
The base is saturated with lot of carrier. That's why this is called saturation region. Fine.
Fine.
Fine. So now we will see what will happen in reverse bias in 10 minutes. Okay. So you are there? Oh, I think he is not there. So when VCB is reverse bias. Okay. So the same case we want to do quickly. It is very easier one. Emitter, base, collector. Okay. So you see okay. So if you see this is plus and plus this is P. Okay. When I apply this forward bias, and I apply this reverse bias. Okay. So if I want to draw the concentration profile, okay. So it will be like this only, no change. Okay. You know, since it is a reverse bias, right? There will be, you know, in reverse bias, what is the concentration here? It will be little bit negative. Okay. So the slope is almost similar. Okay, because you know the del P is equal to Pn0 exponential of VCB by VT minus 1. Okay, since VCB is negative, so this is approximately equal to minus Pn0, right? Theory. So it will be almost the slope will be almost similar. Okay, there won't be much change in slope. Okay, and if I want to plot the magnetic area profile here, because it is reverse bias, right? So if I want to plot the magnetic area profile here, so here it also will be like this. Okay, reverse bias. Okay, so it will be minus NP0, right? Getting?
Getting it.
Okay, so now what will happen? the electron will be injected like this. Okay, this is IEP. IEP. Okay, and similarly I have holes have been injected, right? So this have gone like this. Okay, and you see there is a reverse saturation current, right? So the movement of, since I have a reverse bias, right? Reverse bias means the holes will move from N to P and electron will move from P to N, right? So reverse bias. Okay. This is the recombination current. Okay, so we'll recombine here. Okay, so whatever the slope is there, that will go to ICP, right? ICP. And since you see this is the right, the electron side, this electron will flow like this, right? Not so the electron current will be like this, and they will combine with the hole. Okay, this is ICN. ICN. Okay, so now what will happen? Now IC is equal to ICP, which was there earlier in zero bias, plus ICN. Okay, because you see the electron will flow like this, so the current will flow like this, right or not?
Yes.
So it is same direction as the whole current, right?
Right.
Right. And this IC is nothing but your reverse saturation current. Okay, so it can be written as ICP plus ICO. You know, in a reverse bias, there is a current very called reverse saturation current, right? IS, right? Hello.
Hello, sir. Right.
Yeah. So I can write my IC is equal to ICP plus ICO. CO is nothing but your reverse saturation current, right? We know whenever paying attention in reverse bias, there is saturation current, that is reverse saturation current, right?
Right.
Equal to ICP is equal to alpha I plus ICO. Okay. So this also can be written as, you can go and derive this equation. The same equation can be derived as beta IB plus 1 plus beta ICU. Okay, this is called ICBO. This total is called ICU. Okay, so this equation you derive in the home. Okay, from this equation you derive this equation. Okay, just put I is equal to IC plus IB, then take IC left side, then you can get this equation. Okay,
Okay, fine.
you just put I is equal to IC plus IB, then IC will go left side, then you can get this equation. Okay, so you see IC and IE with base is common, that's why it is ICBO. IC and IB with emitter is common, that's why it is ICU. Okay, fine. Fine. So this is the condition in reverse bias. So you can see the reverse bias is not destroying your transistor action, right or not? Because the profile is almost similar here, right? And what we are getting? We are getting some extra reverse saturation current, right or not?
Fine.
Okay. So the reverse bias is not destroying your transistor action. Okay. So you understood very clearly what is happening in forward bias and what is happening in reverse bias. You understood now?
Yes, sir. Yes.
Yes. So next class we will discuss the small signal analysis of BJT. Okay.
Yes, sir.
Fine. So since it's time is not there now, so I think next class you can complete this BJT chapter.
Okay.
Okay. But whatever we have understood, I have taught today, it is very clear to you, na?
Yes, sir. Clearly.
Okay. So no doubt, right?
No doubt. Sir.
Okay. Okay. So then we will stop today. We will take the next thing next class. Okay.